Good morning, everyone, and welcome to this media webinar to discuss NOAA's and NASA's data for the 2023 global temperature record and other climate highlights from the year. I'm John Bateman with NOAA Communications, and I'll be facilitating today's briefing. NOAA and NASA are two keepers of the world's temperature data and independently produce a record of changes to Earth's surface temperatures based on historical observations over the land and ocean. Consistencies between these two independent analyses and those analyses produced by science agencies in other countries increases our confidence in the accuracy and assessment of the data, as well as the resulting conclusions. Today's 2023 Global Briefing will feature a short introduction by NOAA's Chief Scientist, Dr. Sarah Kapnick, and NASA's Chief Scientist, Dr. Kate Calvin, followed by a presentation of the 2023 Global Climate Analysis. After the presentation, there will be a media question and answer session. We will begin the 2023 Climate Review with Dr. Russ Bose, the Chief of the Monitoring and Assessment Branch at NOAA's National Centers for Environmental Information, or NCEI, who will provide a summary of NOAA's 2023 global temperature and climate data. Following Dr. Bose will be Dr. Gavin Schmidt, Director of NASA's Goddard Institute for Space Studies, who will summarize NASA's global temperature and climate data for 2023. After their presentations, Dr. Bose and Dr. Schmidt will be available for questions, and also the slides from the presentation will be available for download. Just click the link in the download window at the bottom left of your screen. We will now kick off this media briefing with some words from NOAA's Chief Scientist, Dr. Sarah Kapnick.
Thank you, John. I'm happy to join our colleagues at NASA to highlight some of the ways that 2023 was a truly record-breaking year in the global climate record. I'm appreciative of this annual collaborative effort between our agencies. Producing analyses like this helps us gain a collective understanding of how our climate is changing. This information is critical to inform decisions and actions to build both a climate-ready nation to help our communities by protecting lives, livelihoods, and property. This is a core mission of NOAA. But they can also be wielded to improve economic resiliency and innovation as we anticipate and adapt to the changes already experienced and what lies ahead, a duty of NOAA as an agency under the Department of Commerce. NOAA and NASA are able to provide this authoritative global-scale climate data because of continuously collected and maintained observations. Weather, water, climate, and ocean observations gathered from instruments ranging from operational weather satellites orbiting Earth to land-based weather stations to sensors on ocean buoys are the backbone of NOAA's environmental science and stewardship mission. These are the best available science and observations regularly delivered to the American people through this important agency collaboration. I'll leave it to our experts to go into all of the specific climate observation statistics, but I have to pause and say the findings are astounding. 2023 was an extraordinarily warm year that produced many costly climate-driven weather events here in the United States and worldwide. These frequent and increasingly costly extreme events have human consequences, ecological impacts, and socioeconomic effects. The US alone has a record-breaking 28 separate billion-dollar weather and climate disasters this past year, causing over $90 billion in damages. The 28 events easily surpassed the previous record of 22 events set in 2020. Since 1980, the US has been impacted by 376 weather and climate billion-dollar disasters costing over $2.6 trillion. In the US, we have consistently had both the highest total count more than any other country each year and the largest diversity of different types of weather and climate extremes that lead to billion-dollar disasters. This is generally due to a combination of two things. One, a high incidence of many extremes where both exposure and vulnerability are high for producing damage. And two, climate change is enhancing certain types of extremes that may lead to billion-dollar disasters. Our research enterprise will continue to tease apart the specific causes of the observed events of 2023, and we have committed to improving research and data products in response to observed events and damages, which will continue to identify vulnerable regions, help in early warnings for future events, and build equitable climate resilience to extremes. A warming planet, which we'll see plenty of evidence from the statistics provided today, recapping the warmest year on record, means that we need to be prepared for the impacts of climate change that are happening here and now, like extreme events that both become more frequent and severe. This is where NOAA's climate science and services are more relevant than ever before. The vulnerability and impacts of events can be managed if we pair our observations, document changes from the past into the present, and our predictions and projections of the near and distant future. This science and services can be wielded to protect lives, livelihoods, and property to help build a climate-ready nation. As we move to the future, NOAA will leverage its expertise to continue to equitably develop and deliver climate science data and tools from data collected through sharing information with users to support the whole of government effort to address the climate crisis and promote economic development. We are doing this at the local to international scale with publicly available science and strong collaborations that help communities and countries make science-based decisions and build climate-ready nation goals abroad as they shape their climate goals. I'm excited for NOAA and NASA to share this critical climate data with you today. I'm equally excited to see how businesses, communities, and individuals will use this information to enhance our understanding of the world around us and to help prepare for a resilient future. In my capacity as Chief Scientist of NOAA under the Department of Commerce, I'm engaging with key sectors of our economy to promote the uptake of the incredible data that NOAA and the US government provides, with our regular climate statistics being a prime example. Through private sector engagement, public-private partnerships, and work with other agencies within the Department of Commerce and also across the entire federal government, we are also co-developing and supporting innovation in the use of NOAA science, data, products, and technology. In my view, this is a key part of what a climate-ready nation means when decision makers from the local all the way up to the international scale are, as well as the private sector, make use of the foundational work of our agencies, amplifying its impact and fully unlocking its value to society. With that, I'll turn it back over to John for more on today's announcement. Thank you.
Thank you, Dr. Kapnick. We'll now hear from NASA's Chief Scientist, Dr. Kate Calvin.
Thank you, John. In regards to climate, 2023 was a record-breaking year. Last summer, we came together with our partners at NOAA to announce our findings of it being the hottest June, July, and summer on record. Gavin and Russ are going to share more information about the full annual analysis, but it's clear that our planet's climate is changing. I'd like to take a minute to discuss the importance of our research and observations and why it's important to share this information, especially when planning for the future. At NASA, one of our most important missions is our home planet. One way we study Earth is through satellites. We use the unique vantage point of space to see all of Earth. We have more than 24 satellites and instruments in orbit, each of which is designed to measure something different. So we can see things like vegetation, clouds and precipitation, carbon dioxide, and more. We also use surface and airborne measurements to provide a more complete picture of the Earth. And we've been observing the Earth for decades, so we can see the state today and how it's changing over time. And one of the things we're observing is climate change, which is impacting people and communities around the world. In the last year, we saw extreme heat events, heavy precipitation and flooding, wildfires, and droughts. Long-term continuous observations are critical for understanding these changes, and we provide this information publicly so people know what is happening where they live. We work closely with our partners at NOAA in many of these efforts. In June of last year, we opened the Earth Information Center with NOAA and several other federal partners as part of NASA's efforts to support open source science and making data and information as accessible as possible. Collaboration between NOAA and NASA will increase and continue with the upcoming launch of the NASA PACE mission and later when we work with NOAA to launch the next satellite in the NOAA GOES series. NASA's PACE mission will take advanced measurements of sea and sky. PACE will provide unique and never-before-seen views of aquatic ecosystems that feed fisheries, but also introduce harmful algal blooms. PACE will also provide information on aerosols, tiny particles in our atmosphere that affect air quality and influence Earth's heating and cooling. This will build on NASA's 60-plus-year Earth observation record and help us better understand how the planet is changing. And you're going to hear more today from both NASA and NOAA on some of these long-term observations, focusing on surface temperature. Back to you, John.
All right, thanks so much, Dr. Calvin. We will now begin our review of the 2023 Global Climate Analysis with Russ Foes.
All right, thank you, John. And it's good to be back here again this year with Gavin. And thanks for the nice introductions from Sarah and Kate. You've already heard the headline just a little bit. And Gavin and I are going to take you into the gory details, starting with this particular figure. 2023 ranked warmest. Not a surprise, I suspect, to most people at this point, but this figure shows, more specifically, the annual temperature through time from 1980 or 1880 to present, from NOAA's global surface temperature record. The y-axis is the departure from the long-term baseline. So each dot is the temperature for a year, and the blue bars are decadal averages. And just a reminder, both NOAA and NASA, our analyses use surface data, meaning sea surface temperatures from ships and buoys and air temperatures from surface weather stations. We don't use satellite information or weather forecast models in our particular analyses. They're great tools, we just don't use them in our reconstructions. So 2023 was 1.18 degrees Celsius or 2.12 degrees Fahrenheit above the 1901 to 2000 baseline. That beat 2016, the previously warmest year, by a whopping margin, 0.015 degrees Celsius. That's really big. Most records are set on the order of a few hundredths of a degree. So this is a big jump. If you look back at the figure, it's also worth noting the last 10 dots. They represent the 10 warmest years on record. So the last 10 years have been the warmest years on record. You look a little further back at the blue bars, it's clear that each of the past 4 decades has been warmer than the decade that preceded it. And there's been a steady increase in temperature since at least the 1960s and going much farther back than that. Now, as for next year, because everybody always wants to know about next year, well, barring a major volcanic eruption, which we're not pulling for, or an asteroid slamming into the planet, which we're not pulling for either, the NOAA calculations suggest there's a 1 in 3 chance 2024 will beat 2023, and 99% chance that it'll rank in the top 5. But now, for the sake of full disclosure, because those who do predictions often don't talk about their records, last year at this time, we were saying there was only a 7% chance that 2023 would be the warmest year on record. So the point is you have to take these things with a grain of salt. But the bigger point here is all of this is consistent with increasing concentrations of heat-trapping gases. Carbon dioxide concentrations are about 50% higher than at pre-industrial levels. Methane's up about 150%, nitrous oxide about 25%. Present-day concentrations of carbon dioxide are elevated levels, basically higher than at least the last 2 million years. And there was one recent study that said it might be higher than the last 14 million. So it's been a long time since they've been this high. There are some other factors that certainly contributed to the heat in 2023, and Gavin will go into these, I'm sure, in more detail. But one is the whole notion of this transition from La Nina in the Eastern Tropical Pacific to a strong El Nino by mid-year. El Ninos, of course, tend to have a warming effect for a couple of reasons. The tropical Eastern Pacific is a big chunk of the Earth's surface. That's a lot of area to be above normal. And then El Ninos can cause droughts in other areas. And when it's dry, it's easier for surface temperatures to heat up, which also helps make it warmer. A couple of other things, the long-term aerosol emissions, those tiny particles that Kate had mentioned, aerosols have gone down. Aerosols reflect sunlight. The decline has probably contributed at least a little bit to higher temperatures this year. And then there was the volcanic eruption in Tonga in 2022, which spewed a large amount of water vapor into the stratosphere, and that may have had a role in nudging things up this year. But that's where I stop. I'm going to hand the torch off to Gavin.
Thank you very much, Russ. You gave a pretty good summary. Our data is very similar to that of NOAA's. The top line numbers and the difference that 2023 was compared to the previous record is slightly different, but we're talking very, very small differences there at the 100th of a degree level, so that's not really significant. I think it's worth pointing out that our uncertainty on the annual mean anomalies is around 0.05 degrees C, and so the distance by which 2023 beat the previous top years, which in our record were 2016 and 2020, is clearly above the measurement uncertainty. And so we're looking at this, and we're frankly astonished. One of the things that we have historically liked to do in these briefings is give a little bit of a story about why any one year is different from any other year. And there are a lot of candidate stories this year, but none of them really work. As Russ pointed out earlier, the predictions that we had at the beginning of the year, because we were starting with a La Nina phase in the tropical Pacific, were that this year would be pretty much on trend, and with only a small chance of being a record warm year, and that's not how it worked out. And this has been very, very unusual, and I think we'll see as we go forward quite how unusual this year was. Russ.
All right, thanks, Gavin. Now we're going to take a look at a map, if you will. This is the NOAA's map for temperatures in 2023. Reddish areas had above average temperatures, and bluish areas were below average. And the baseline period here is 1991 to 2020, basically the last 30-year normal period. As you can see, temperatures were warmer than average, meaning reddish in color, over the vast majority of the Earth's land surface in 2023. Areas of notable warmth included the Arctic, northern North America, and Central Asia. North America and South America and Africa each had their warmest year on record. Europe and Asia ranked second. And overall, it was the warmest year on record for the land surface as a whole. Much of the ocean surface was warmer than average as well. The North Atlantic and the Eastern Tropical Pacific stand out in this regard, again, the latter owing to El Nino, which developed last year and is still growing strong. Overall, it was the warmest year on record for the ocean surface as well. The tiny map in the lower left tries to put this heat in perspective, and I deliberately made it tiny because all I want you to see is the fact that most everything is red. Anything that's reddish, when meaning most of the planet, was much above average, meaning that like the temperatures in those respective areas were exceeded the 90th percentile for that location. This is pretty unusual. It was pretty hot. But there were, as always, some places that were cooler than average, meaning bluish in color, but the areas were relatively small. Eastern and Western Antarctica are good examples. And parts of the Southern Ocean near Western Antarctica were below normal, as was Southern Greenland. So now back to Gavin, who's going to give you a similar map, but for a slightly different baseline period. So his map's going to look just a little different.
But the basic picture is the same. It was warm everywhere. This is with respect to the 1955 to 1980 baseline. So there's been more global warming. So you can see that clearly. You can see clearly the effect of El Nino right on the tropical Pacific. But you can see that the warmth extends far beyond the tropics to northern hemisphere land, the Arctic, and the rest of the world. What we're seeing is a pattern that is broadly predicted. The long-term patterns are broadly predicted. We expect more warmth over the land than the ocean. We expect more warmth in the north than in the south, and we expect most of the warmth to be amplified in the Arctic. And when you take the longer view, this is what you see. And so that part of what we're seeing is quite well predicted and is in line with our long-term expectations for how the climate will be changing given the changes in greenhouse gases and other forcings. But the specifics of this year are quite different, as I said. Russ.
All right. Now we're going to spend just a minute or so looking at a movie for the year. What we've shown you before is basically the average picture for 2023, but there was a lot of variability through the year. And that's what this animation is here to demonstrate. And again, it shows you the departures from average for each particular month. And the basic message here is things that got hotter as the year went on. Early in the year, which is where we are now, there were some large land areas with below average temperatures. such as over Eastern Asia and North America. That's somewhat typical. You're going to have some areas that are below normal and some that are above. There are also large areas, global ocean with below average sea surface temperatures, such as the tropical Eastern Pacific and the Indian Oceans. But by about mid-year, things had calmed down, meaning the big intense areas of blue and red had faded somewhat, which is somewhat typical. Departures from average are smaller in the Northern Hemisphere summer. But what you started to see in mid-year was that the global oceans increasingly warmed up. Meaning they turned pinkish and reddish. This really stands out in the tropical Eastern Pacific, which again is capturing the transition from a waning La Nina to an El Nino. And then you saw the land areas warm up as well. In the end, every month from June through December, each ranked as the warmest month on record. The global ocean was record warm for 9 consecutive months, meaning from April through December. The July global temperature value was likely the warmest of all months on record. And the September anomaly value was probably the largest departure from average for any month on record. So if you want to think of things as a horse race between, say, 2023 and the next warmest year, which is 2016, things went like this. 2016 was the pace setter early on. It was substantially ahead of 2023. But 2016 started to lose steam as it rounded the first turn, meaning in springtime. And then 2023 continued to gain ground in the backstretch, meaning it was leading by a nose by late summer. By the end of the race, 2023 won by a long shot. It was the largest margin of victory on record, but it was no ways any kind of photo finish. Okay, that's enough of the video for now. Let's go ahead to the next slide if we can. Gavin.
So this is where it starts to get a little bit both interesting and perhaps a little discomforting. We have traditionally seen the picture of the long-term trend of the record being a contribution of the long-term trends, which we think we understand because of the changing climate, and then the ups and downs in any one year, which have been historically related to volcanic eruptions or the state of ENSO. And the way that has worked historically is that the state of ENSO in the spring is the biggest predictor of what the whole year will be. And so when we kind of pull out the state of ENSO in February and March, that generally reduces the uncertainty and it makes it look like a less noisy. It's a big contributor to that interannual noise. But remember that in February and March, we were still in a very mild La Nina phase. And so that would have predicted that 2023 would have been slightly cooler than the long-term trend. And yet, it was quite a lot warmer. And so the expectation that we had about how ENSO affects the global temperature and the time lags that we normally expect was totally reversed this year. And it's kind of easy to say, okay, well, you know, we were coming into an El Nino towards the end of the year. But the El Nino that we're seeing is not an exceptional El Nino. It's not a bigger El Nino event than 2016. And in 2015, when we were ramping up to that big El Nino, we saw a change in temperatures that were less than half in the global mean than what we've seen in 2023. And so if we're going to claim that 2023 was because of the ongoing El Nino towards the latter half of the year, you have to then explain why that's never happened before, right? We've had El Ninos before, we've had bigger El Ninos before, and they've never had that kind of impact on the global mean temperature. So either this El Nino is different from all other El Ninos, or the system is responding differently to how it's responded to all other El Ninos, or there are other factors going on that are kind of coincident with the El Nino, and that could be factors associated with the warming in the North Atlantic. So the record temperatures that we saw in the North Atlantic started before El Nino had really got going, and so that seems to be an independent thing that's going on. The changes that we saw in Antarctica, particularly the very, very low sea ice levels during their winter, so during the Northern Hemisphere summer, again, does not seem to be related to El Nino, but was a contributor to the very large warmth that we saw starting from kind of July and onwards. So our normal story, our normal explanation for what's going on does not work this year, and I think that there is a lot more work that needs to be done to really understand what happened in 2023. In 2024, we'll be seeing whether this persists or whether it kind of goes back to a normal pattern, and that will be kind of telling as to whether 2023 was just a very unusual combination of things that all added up to what we saw, or whether there's something systematically different going forward. That uncertainty in the explanation, as a scientist, is kind of exciting, because we're excited by novelty and things that we have not been able to understand. But given that we're talking about the world's climate and ongoing climate change, it's also a little bit disconcerting. And so I think the word is discomforted by the findings that we've had, beyond just, oh my gosh, another record warm year. Anyway, Karen, next.
Yeah, so it's not been a little drama year to be a climate scientist. I think that's what Gavin's trying to say. I'm going to change gears here for just a minute, because Gavin and I, to this point, have spoken mainly about temperature, and there were a number of truly notable extreme heat episodes this year, such as the Texas and Louisiana, which really, really had a long, hot summer. But there have been plenty of other things going on this year, and that's what this map is here to illustrate. It's just sort of a collection of the major events that took place this year, and I'm going to speak to ones that are primarily related to not temperature. Like, for example, in January, there were 9 back-to-back atmospheric rivers that pummeled California. It brought a total of 32 trillion gallons of rain and snow to the state, which was great for reducing drought, but had a profound impact. February and March, we saw Tropical Cyclone Freddie. It was one of the longest living tropical cyclones on record. Traversed the southern Indian Ocean for more than 5 weeks. It had major impacts on Madagascar, Mozambique, and Malawi. Beginning in March and continuing across much of the summer, wildfires across Canada burned more than 45 million acres, which was 2.5 times the record of Canadian wildfires before. Actually, for North American history, I think. These fires caused widespread air quality issues throughout much of Canada and the US for a good chunk of the year. In August, winds from Hurricane Dora exacerbated a wildfire on Maui that destroyed a historic town. I'm sure everyone heard about that, and it became the deadliest wildfire history in the US in over a century. In August, there were prolonged monsoon rains that caused an overflow of a major river in Pakistan and India, which flooded hundreds of villages and prompted the evacuation of more than 100,000 people. Then in September, we had Storm Daniel in the Mediterranean, which brought strong winds and an unprecedented amount of rain to eastern Libya in particular, which caused massive destruction, including burst dams across many towns, and led to the death of more than 10,000 people. And there were many others. So, another year of extremes, but I wanted to mention a couple of things here, clarify a couple of things. First of all, we aren't saying that any of these things were caused by a change in climate. Extreme events have always been a part of the climate system. And it's important to note, and I believe that Dr. Kapnick said this earlier, that there are more than one thing that contributes to an extreme event. Part of it's the event itself, and then part of it's changes in exposure, meaning who or what lies in the path of an event, and vulnerability, meaning their ability to cope. Both of those things can exacerbate the impact of extreme events. And as she mentioned, there's been an upward trend in billion-dollar disasters in the United States, and that's due to a combination of changes in climate and changes in exposure and changes in vulnerability. So we certainly expect to see more extremes in a warming world. And in theory, climate change could have worsened some of the events this year. But individual events have complicated and particular circumstances that need to be sorted out, which is on the frontier of science. And you'll probably see some more work trying to diagnose that as we move forward. Now back to Gavin.
I think it's as we talk about what's going on. I have two graphs here, which are of relevance to what we're doing. Obviously, the Arctic sea ice has been declining for decades now. This year had a decrease that was basically in line with those long-term trends. Though there is a fair bit of interannual variability that can fool you, I think, if you're looking for reasons to think that things are not changing. But both March, the winter extent, and September, the minimum summer extent, are falling in line roughly with expectations. The temperatures that we see in the Arctic depends a little bit on how you exactly define the Arctic, but taking the 64 to 90 degrees north area, the Arctic is warming about 3.5 times faster than the global average. And depending a little bit on the definition and exactly where you do it, you can end up with anywhere between 3 and 4 times faster. I still see people referencing very old stuff that suggests that the Arctic was only warming twice as fast as the global mean, but that has not been true for many years, and we should stop saying that. If you go to the next slide, I want to point out that Antarctic sea ice trends are also changing, and are also changing in ways that are a little hard to pass. So through to 2014, Antarctic sea ice extent was actually increasing. We have some work that I'm not really going to go into here, suggesting that was actually related to the amount of meltwater coming off the continent, which increases the stratification and leads to more sea ice being formed, but subsequent to 2014, we saw a very rapid decline in 2016, 17, 18 to what were near record lows, a slight recovery, and then this year an absolutely massive low sea ice extent during the time of normal maximum sea ice extent in Antarctica, so that it's effectively an off the chart estimate. And again, and something that was not expected or anticipated. And so one other element of why 2023 is so interesting. This is we don't know. I mean, there's been claims in the literature that this is now a new situation, and that it will continue to be low like that, as some of the models have been predicting. But I think that the Antarctic oceanography and ice sheets and sea ice interactions are something that the models have generally not done a great job with. So I don't know how much weight one should give to the model predictions for Antarctica right now. But things are very different in Antarctica, and again, if things go back to normal, then we will look at this as a combination of blips and just the roll of the dice, but there's a danger that it won't go back, and that this is actually the start of a new phase, and that again is obviously quite concerning. Next.
All right, thanks, Gavin. Changing gears a little bit here, ocean heat content. The slide shows ocean heat content from the late 1950s to present. Ocean heat content is basically the total amount of warmth or heat energy stored in the oceans. It's essential for understanding and modeling global climate because the oceans absorb more than 90% of the excess heat in the Earth system. Changes in ocean heat content are determined using measurements of ocean temperatures around the world at different depths. These measurements come from a variety of instruments ranging from things that are called bathythermographs to gliders to bottles, and even in rare cases, some marine mammals have been instrumented and sent down to measure things. In 2023, the warmth of the world's oceans hit a record again. It's the highest since records began 6 days or decades ago. By the way, this time series is for the top 2,000 meters of the ocean. The 5 highest heat content values have all occurred in the last 5 years, and there's been a steady upward trend since about 1970. And as with surface temperature, each decade has been warmer than the decade that preceded it. But there's less variability in ocean heat content. It just sort of keeps stacking up. There are multiple estimates of ocean heat content. NOAA has estimates. There are estimates outside the United States. NASA has some estimates from the ECHO record. And all of those are consistent in showing an ongoing increase and record levels of ocean heat content this year. Now, because changes in ocean systems occur over really long time periods, like centuries, the oceans haven't yet warmed as much as the atmosphere, even though they've absorbed like more than 90% of the Earth's extra heat since the mid-1950s. If it wasn't for the oceans and their large heat storage capacity, the atmosphere actually would have warmed even more rapidly. And there are, of course, implications to this, like warmer ocean temperatures provide heat for tropical cyclones. They affect the frequency and intensity of marine heat waves. And because water expands as it gets warmer, it contributes to the ongoing increase in sea level. Now back to Gavin.
So we're often asked how reliable the surface temperature assessments of global temperature are, and there we have for the more modern period we have the possibility of evaluating those trends against both reanalyses, which are weather forecasts, which bring in a lot more data from satellites and radiosondes and things, but don't use quite the same data that we have, but also direct measurements from satellites. And so you can look here at the top row is the comparison of the GIS temp trends from 1979 to the present compared to the ERA5 reanalysis from, again, 1979 to the present. And the rates of change are very similar. The patterns of change are very similar. And so we can see that the reanalyses have slightly more resolution. There isn't as much smoothing that goes on with those, but the overall patterns are very, very close, and the trends that we see are not obviously different, and statistically they're identical. So we can have pretty good confidence that the surface temperature networks and the processing that goes with that are consistent with what we would see with the state-of-the-art reanalysis systems. And then for a totally independent view, we have things like the AIRS satellite, which gives a measure of changes in ground temperatures, so both over the ocean and over land. And they're a little bit more, they're a little noisier. It's a shorter period, 2003 to 2023, so that's a 21-year period. But again, you can see in the bottom row that the overall patterns, once you take into account the fact that the surface temperatures products are slightly more smooth than the satellite data is, the patterns are very clear and very similar. Though there are some notable differences. But again, the trends are all consistent, and that's a totally independent estimate of those changes over time. Russ?
All right, and the last slide in our presentation today, basically this is going along the same lines that Gavin just was going on about in terms of validation, if you will. There are other groups around the world that track global surface temperature. The the UK Met Office Hadley Center has done this for a long time. More recently, you've seen some fine work from the Copernicus Climate Change Service. Berkeley Earth has been doing this for some years, as has the Japan Meteorological Agency. This figure shows the time series for 4 of those major analyses. And despite using somewhat different data sources and analytical methods, the results rarely diverge by much. They all say 2023 was the warmest year on record. And then there are other groups, parts of NOAA, remote sensing systems, and the University of Alabama in Huntsville that track atmospheric temperatures, meaning temperatures above the surface, deep slabs of the atmosphere, if you will. This slide doesn't include those records because they only go back to 1979, but the satellite records also show that 2023 was the warmest year on record, and again, by a large margin. For example, if we take the University of Alabama in Huntsville time series, they have 2023 as being approximately 0.12 degrees Celsius warmer than 2016. Not as big a difference as in the land records, the surface records, but still a very, very large margin. A couple of other points here before we wind down. One is that there has been some work done that averages these various analyses together to try to get a better sense for how 2023 compares to the 1.5 degrees Celsius threshold that's been talked about, of course, in the Paris Agreement. And if you average the 4 together, you're starting to get pretty close to 1.5 degrees in 2023. You're not there yet. And 1 year above 1.5 doesn't mean that we've crossed that threshold permanently, but the message is that things are starting to approach that threshold, which is, I think, projected to happen on a sustained basis sometime in the 2030s or 2040s. But we always take our projections with a bit of a grain of salt. And one last thing, this is not shown on the plot, but it's still worth noting. It's certainly warmer now than any time in the past 2,000 years. And you probably heard some recent stuff that talks about the last 100 or 125,000 years. That may be true. It's certainly awfully warm. The next warmest period was about 6,000 years ago, which was a little warmer than pre-industrial, but not as warm as today. But basically, it's as warm now as it's been in a long time. And that's not a trend that we expect to continue. It's not a trend that we expect to change anytime soon, because there's no forces known to science that would, at this point, alter that. So I'm going to stop there. And I think this is the point at which Gavin and I take questions, and Gavin corrects me on those things that I might have gotten wrong.
All right. Thanks so much, Russ and Gavin. We'll now open the briefing to your questions. We have about 17 minutes left to ask those questions. To do that, all you need to do is find the Q&A box located at the bottom of your screen. Please type in your name, affiliation, your question, and the specific expert you would like to answer that question if possible. And as a reminder, we will have Dr. Vose and Dr. Schmidt available for your questions. We already have a question in, guys. This one I think is for either Gavin or Russ. This is from Craig Miller from PBS Next Avenue. Can you speak to the Jim Hansen assertion that climate breakdown is accelerating well beyond expectations? I mean, who would like to take that one?
So we have one extraordinary data point that is a little bit hard to explain. Until we have a better idea about exactly what was going on in 2023, it's very hard to say whether that means that whether that was a blip or whether there's something systematic that's shifted. I think it's too soon to tell. While one is free to extrapolate, I think the history shows that extrapolating from effectively a single data point is not usefully predictive. I'm very much in a we need more information mode, and we're going to be working. We're going to be working quite closely with colleagues all around the world to try and see exactly what was going on in 2023 and what is continuing to go on now. I would not make any further claim beyond that.
I'm going to add one note to what Gavin said, and this goes back to the theme of coming clean on predictions. First time Gavin and I did this in 2020, I made some comment about, there's a hint that maybe there's a bit of an acceleration in the rate of warming. And then, of course, we had 2021 and 2022, which were less remarkable in their ranks. And now we have 2023. So it's a bit of whipsaw game, if you will. And I think that's one of the reasons that Gavin emphasizes some caution here in talking about that sort of, is there an acceleration in the warming itself or the larger climate system? You know, it's easy to get excited when we see a big year like this, but it's important to take a step back and really try to get a grip on what's going on.
Yep. Thank you so much, guys. We have another question. I don't know if we're able to go back into the presentation slides because I believe this was referring to some slides earlier in the presentation. So if we can do that while I ask this question, that might be helpful for reference. But Jim Siegel had the question, if you could explain what each dot is, that is, how was each dot calculated, the inputs, etc. I'm sorry, El Nino map is what he wanted to get to, if you could find the El Nino map. And if Gavin or Russ, if either one of you would like to explain that.
This one? Well, okay, so I made it, so I should explain it. There's two lines there. The black line is the GISTEMP record that we presented earlier on, and then the red line is a statistical estimate of what would have happened if we hadn't had if it had been a neutral El Nino year, right? So it's trying to it takes out the linear regression associated with the ENSO state in the spring, and then removes that. And historically, that had reduced the noise, right? So you can see, for instance, in 2016, 1998, that are pointed out there, the estimate, ENSO corrected estimates are all lower than the actual numbers, right? Because El Nino in the spring gave a warmer temperature in the annual mean, and you can see the same thing for the La Niñas. But then when you have years that end in an El Nino, so you have an El Nino building, so that would be 2015, 2009, 1997. Sometimes we can get record warm years, but we don't get record warm years that are so large, and that's very different to what happened in 2023. So 2023, you can see that the corrected line is actually higher than the actual line, suggesting that that 2023 was anomalous beyond anything that we've seen. And you can see the years going back, that's never happened before. And so there is, I mean, I played around with, other statistical models where, you take the historical data up to, but not including 2023, and you see, okay, by using different predictors like ENSO later in the year, can I make a better estimate of what would have happened in 2023? And the answer is no, I can't. So hopefully that is more clear.
Yeah, thank you, Gavin. We did have a follow-up question. I think this is for either one of you, also from Jim Siegel. When you say that the temperatures are the warmest on record, how far back is that? 1880? How are the data from the earlier years, for example, the 1800s, adjusted for the fact that the most recent years, the 2000s, may have more points of measurement, satellites, and higher accuracy, etc.?
Maybe I could say that. So Russ gave a good estimate of a good description of what the data is, but I just want to talk a little bit about the uncertainties. And there are uncertainties in all of these measurements. They come from the spatial distribution of the temperature stations, the time sampling of where there were boats and where there were measurements, and that gets those uncertainties get larger as we go back in time. So the uncertainties right now for the annual anomaly are around 0.05 degrees Celsius for any one annual mean number. And as you go back in time, in the 19th century, it's closer to 0.15 or 0.2. So the uncertainty increases by about a factor of 4 as you go back in time. And that's mainly because we have less information from the Southern Ocean and the Southern Hemisphere altogether. And so that uncertainty is something that we take that we try and do a very good job of understanding. We have a new paper that's in preprint that discusses a new ensemble of GISS temp reconstructions that tries to sample all of the uncertainties in the homogenization, in the sampling, in the accuracy of the temperatures themselves, and so we worry a lot about that, but none of those uncertainties are large enough to change the bottom line of what we're talking about, and that's the long-term trend and the record warmth that we're seeing in 2023.
Two quick things to add on to what Gavin said. I think part of the question was also how far did this record go back? NASA goes back to 1880. NOAA goes back to 1850, and I won't go into great detail, but yes, there are many more observations today than there were back then. And there's quite a bit of work done to make sure that we take that into account. And if you go back to, say, 100 years ago when there are less observations, a lot of the work involves making educated, informed guesses as to what's going on in places where you don't have information. So that's all part of the soup making, if you will.
Well, let me finish with one point there. I mean, we can reduce those uncertainties further if we support efforts to do data rescue. There are millions upon millions of both weather station and ship log measurements that are written down that have not been digitized, that as that happens, we will be able to reduce the uncertainties going back in time. And that will come up. I'm sure people will ask us a little bit about the warming since the pre-industrial. Some of the uncertainty associated with that can be reduced if the weather services all around the world and the data rescuers all around the world can be supported to pull more data into these databases.
Okay, thank you guys. Thank you both. We have another question. Either one of you feel free to jump in and answer. It is from Andrew Friedman from Axios. Were the margins of warming in 2023 versus all previous years largest? In other words, did this year warm faster than any other year in NASA and NOAA's data? Also, thanks for doing this presser.
I'm not sure I understand the question exactly. If you're asking if like the rate of warming from, say, January to December was faster than in any other year, I can't say we've gone back and looked at that. I can say that like the margin of victory, if you will, between 2023 and 2016, that difference was bigger than any difference we've seen before. But I may be misinterpreting your question.
I'll be happy. I was trying to do that while we were talking, and I have a little thing on the side, but I can't quite do it and concentrate on this. But I'll be happy to email you the results of that after the presentation.
And thank you guys. And again, at the end of this, I'm going to remind people how they can reach out to me with any questions we don't get to, and I can send them off to both of you guys to answer later. So stay tuned for me to remind you how to do that. Another question we have coming in from the Atlanta Journal-Constitution from Maris Lutz. Dr. Calvin mentioned that NASA uses satellites to track carbon dioxide in the atmosphere. Can you elaborate about how NASA measures greenhouse gases in the atmosphere? And is that something that can be seen in satellite imagery?
Well, I guess I can take that. So we have OCO and a series of satellites that measure carbon dioxide from space, and we have right now we have one instrument on the International Space Station that is tracking that, and that allows us to see with great precision how much column carbon dioxide there is, and so you can see the the seasonal cycle. You can see the changes year by year. And that of course you can see from space. We also have the EMIT instrument, which nominally is looking at dust, but has spectral resolution for methane as well. And so that is able to see hotspots of methane, and those are mostly leaks from mining, oil and gas processing, and seeps. So you can see, hotspots where there's a large methane leak, and we're using that. There are other satellites that are looking at that as well. GHGSat and Sentinel-6 can see some of that as well. And those are being used to kind of track down leaks and help people fix them in very short order. So yeah, we are tracking carbon dioxide and methane measurements and methane concentrations in the atmosphere from satellites that complement the ground-based networks that NOAA runs in places like Mauna Loa and Scripps and Cape Grim and the like.
All right, thank you, Gavin. We do have a question here from the New York Times from Delger Erdanasana. Hopefully I'm pronouncing that correctly. It says, I'm wondering how each agency chooses what years it will use as a baseline for comparison. I think the EU Copernicus goes back to the 1800s. Is that why the results are higher? How do you or organizations like the WMO then go about reconciling these against a common baseline?
Okay, so let me make one thing clear. The internal baselines that we use are basically just there for historic purposes. It's where we started, but really shouldn't be of great interest to anybody else. When we put all of these things on the same baseline, right, that's when we can compare these things. And when we put things on the same baseline, they line up a lot better. Now, the Copernicus data doesn't actually go back to 1850. The Copernicus data is a reanalysis product that goes back to 1940. From 1940 on back, they're using a match to the Hadley CRUT data, which comes from the UK Met Office and the University of East Anglia, and they're kind of tacking that on to make an estimate of how things have changed from the present day to the pre-industrial, which we're nominally describing as 1850 to 1900. There is uncertainty about what that baseline is, and so the NOAA baseline there is around 0.2 degrees warmer than the Hadley CRUT baseline, and that's a function of the different sea surface temperature products that go into these assessments, and that's a real uncertainty. We don't know what 19th century temperatures were like better than to about 0.2 degrees Celsius. So the numbers that were the headline numbers from the Copernicus data, which was I think 1.48 above the pre-industrial, that comes with a certain degree of uncertainty. The equivalent numbers for NOAA and for NASA are around 1.34 to 1.36 warmer than the pre-industrial, but that's mainly due to differences in how we interpolate back through the 19th century, but also in the SST product that we're using. So WMO has a little formula for putting these things all together. They take an average of the modern things and they kind of stitch it to an estimate with some uncertainty for the pre-industrial level. And I think that their press release had 1.45 plus or minus 0.12 with respect to the pre-industrial, and that's a fair assessment of where we are.
Thank you. Thank you so much, Gavin. We're getting close to the end of our time. We're going to take two more questions for you guys and then wrap up this media briefing. Next question is from Seth Borenstein from AP. This is for Gavin. Can you show monthly changes in ocean heat content and how much or could ocean heat content be driving the anomalous readings in 2023? And is it more crucial than ocean surface temperatures?
So ocean heat content, is not more crucial than ocean surface temperatures. So ocean surface temperatures are what we're trying to assess when we're doing the global temperatures. And the ocean heat content increases are mostly below the surface, and so that can increase. And the SST is somewhat independent of that, though obviously it is related. I see the increases in ocean heat content not so much as a cause of change, but as a validation of why things are changing. Right. So we think things are changing because we have increased greenhouse gases. That's changed the energy balance at the top of the atmosphere. Greenhouse gases have made it such that more energy is coming in than is able to leave. That energy has to be stored somewhere in the system. It can't be stored in the atmosphere because it has such a low heat capacity. And so most of that energy is being stored in the ocean. And so the increases in ocean heat content are telling us that energy imbalance is large and is growing, which is in line with what we expect from the increases in greenhouse gases. But in and of itself, it has local impacts on ocean circulation and biology, but it isn't in and of itself what's causing the atmosphere and the surface to.
Thank you. And then our last question, either for Gavin or Russ. This is from Sabrina Shankman from the Boston Globe. What was behind the high ocean surface temperatures in the North Atlantic this year? Thank you.
I can take it, but
you can have that one, Gavin. That's your space.
Okay. So if you recall, the high ocean temperatures in the North Atlantic started in the spring in March and have basically increased ever since then. It's interesting what caused that. So there has been claims that this is related to changes in marine shipping emissions that have reduced over the last few years because of better regulation from the International Maritime Organization. That's a plausible argument. We have got evidence that those emissions have fallen by about 80% in the last 3 years, and so that would, everything else being equal, be expected to lead to warming. But when we've done the quantitative estimates of that, now putting in those changes in the aerosols, seeing how the temperatures change, you don't get very large numbers. You get something like 0.1, 0.2 degrees in the North Atlantic, maybe 0.05 degrees in the global mean. It's not very large, and the reason why that is because the marine shipping emissions, they're a large component of the anthropogenic flux into these areas, but they're not a large component of the total amount of sulfate. Most of the sulfate is being produced by plankton through the production of dimethyl sulfide, which then oxidizes in the atmosphere to produce sulfate aerosols. So that's a natural part of the sulfate. So we're seeing a change in the anthropogenic burden, but we're probably not seeing a very large change in the total burden. And so the impacts that has both directly through the absorption and the reflection of radiation from the aerosols themselves, but then their interactions with the clouds is not expected to change by the same order of magnitude. There are other things that could be going on. Early in the spring, we had a very anomalous North Atlantic oscillation pattern. We had a very anomalous lack of Saharan dust that normally goes across the North Atlantic, which is a cooling thing. So it's possible that we're looking at the North Atlantic at something that was both triggered and perhaps amplified by internal variability, but perhaps there's also an anthropogenic component in that as well. That's part of the research that people will be doing in the months to come.
Thank you once again, Gavin. All right. As always, you both were a wealth of information today. We appreciate you guys being on for this press briefing. We're going to wrap it up right now as we are 5 minutes after the top of the hour. I'd like to thank all of our presenters and participants for joining us today. As a reminder, a recording of this media briefing will be available later today at the online media advisory, as well as on the YouTube channel. If anyone has additional questions or informational needs from Russ or Kevin, you can reach out to me at my email. My name again is John Bateman, and I'll spell that email address for you. It is nesdis.pa@noaa.gov, nesdis.pa, as in public affairs, at noaa.gov. My contact information is also available in the media advisory. Thanks everyone for joining us.